Can everybody hear me?
Yeah.
Yep.
Good. You guys ready for an exciting class today? I'm excited to see how these breakout rooms do. I don't know who G. Durr is, but they're excited. Is that George?
Are the breakout rooms just randomly assigned, or how did you decide on this?
They're going to be randomly assigned because I didn't want to go in and click them all. So you're going to probably be with people you've never been with before. I tested it out on my family today. Okay, let's get started. Looks like it's 2 o'clock on my phone at least, or on my computer. I'll say a prayer, get us started, and then we'll get going. Father in heaven, we are grateful that we can pray as we begin our class today. We ask you to help us to learn well, have the Spirit. Bless the students especially, that they can feel like they learn this material and that they can still master these concepts even though we're in this distance learning mode. We pray that this virus will be slowed and that cures can be found. We pray that the economy will be able to bounce back, that jobs will be there, and that most importantly, that thy work can go forth. And we say these things in the name of Jesus Christ, amen. Okay, so what you see on your screen right here is something that's on Learning Suite. You can download it. I probably suggest you do that so that you can have the problems always with you. We've got, let's see, it looks like we got about 60 people here. I think we can either divide up into groups of 5 groups or 10 groups. You can see if we do 10 groups, I've got it listed here that groups 1 and 6 would work on problem 1, 2 and 7 work on problem 2, and so on. And what we'll do is kind of like what we do in class when we solve these out. You guys can work together, you get some paper at home, see if you can work through these. I've selected these problems specifically because they can be worked by hand with just a calculator. And so in a non-online class, the final exam would be no computer because it would all be given in class. With this class, I still think I want to do it without most computer, not saying you couldn't use it, but I won't specifically design problems that require you to use the computer because I don't want you to get bogged down in solving computer type problems on the final. And so Mark's thinking we do five groups of 12 students. Does that sound good with everyone, or do you want to do smaller groups? Some people say 10 groups to do smaller.
I would do smaller groups.
Most people are saying 10 groups, smaller groups. Okay, here's what we're going to do. When I do breakout rooms, I get to automatically assign you. I don't know who is going to get put in what, but there's going to be about 6 or 7 people in each group. And you'll get a little invite that says, do you want to join a group? When you join that group, you'll be only shared with those people in your group, but you can talk to me by chat or invite me into your group. And if you have some questions, and I at least have something that I can tell everybody something, just like a written announcement. So you can look for those, but I've never had a class not get all 5 of these done within the allotted hour. So we'll let you work on them a little bit. You can ask me questions, and here now, I've got the rooms all ready to go. And you should have gotten invites to the breakout rooms, and you want to say join. Yeah, so I see a few people joining. Good, good, good. I don't know if everyone can still hear me, but I'm going to broadcast a message to everyone. Let's see. Ben, I think you just came in. I don't know if everyone can hear this, but Ben, are you on? I need to assign you to a group somehow. I'm going to see if I can do that.
Yeah, I think I'm just by myself right now.
Let's see what I can do. I'm going to assign you just to a random group here.
Okay.
You should get an invite here. Did it come up on your screen? Good, okay. Josh, you just came in. I'm going to assign you randomly to a group. You're going to want to accept that invitation.
Okay, that'd be great.
You should get an invitation here pretty soon if you haven't got it already. George, I think you invited me into your group. Do you have a question?
Oh yeah, I'd invited you when we weren't sure. Or is group 5 doing problem 5?
Group 5 is doing problem 5, yes. Do you
Okay.
see my screen still?
No.
Okay, yeah.
No.
So I will broadcast a message to everyone, but you're doing 5. Yeah, problem 5.
Okay, perfect.
I can't hear you on my end.
I don't know if everyone can hear you.
think we have enough information actually.
Oh, because we only have one unknown. We only are searching for the out.
Mhm.
No, length and out, so we have two unknowns.
Yeah.
Yeah, so the two equations that we use are the Q equals UA log mean or whatever, and then the cold stream, the water stream.
And
The
MC
cold
delta
stream
T.
equals the UA log mean, actually.
right, so just have two.
Group 2, just checking in on you guys. Are you guys okay?
Yeah. Yeah,
Good.
we're doing well. We were looking, just talk over the problem. We're looking at an example from lecture 28, finding the surface area.
Okay.
The only thing that we're unfamiliar with, but I think we can figure out, is the problem says that it's a it's a cross flow heat exchanger with both fluids unmixed. So we're looking for the I think in who was it that said in lecture 28, or we have the table for no, is that right?
We're
Effective
thinking,
relations.
Yeah, do we use NTU?
So you could theoretically use log mean temperature difference. You'd have to look at the supplementary information to get the right F, but it might be easier just to use, since you're doing this by hand, like figure 11.14 is cross flow, both streams unmixed. If you look at figure 11.14, that's how you could get relate your NTUs and your epsilons. And that might be the little easier route here.
That's kind of what we were doing.
Okay, great. I'll let you guys get to it then.
Thank you.
oh, wait, Dr. Knotts?
Yeah.
So for it looks like we're dealing with air and water. We're just supposed to get the heat capacities from the book, right?
Yeah, I would just use the book for right now. So guess a reasonable temperature, heat capacity to do your big CC and your little CH, or your big CH.
Mm-hmm.
And you're probably going to be close enough that you don't need to iterate.
Okay.
Okay.
Sweet. Thanks.
So
because if that's what you're talking about, I think that's only for shell and tube heat exchangers.
Okay.
Hey, group 3, I'm just checking in on you guys. How you doing? Do you have any questions? Do you guys hear me?
Yeah.
Yeah,
Okay.
we can hear you.
You guys feel like you're getting problem 3? Just want to check what problem 3 is. What method are you going to use? Are you going to use epsilon NTU or delta T log mean for this one?
We haven't decided, but delta T log mean sounds good.
Okay. You can use either one. In this case, it's pretty easy because you have all the temperatures and you have 3 of the temperatures, right? But you can get the third one if you wanted to fairly easily, or the fourth one. Okay, I'll let you guys keep going then.
Right.
Hey, group 7, just wanted to check in on you guys, see how you're doing.
Hey, Dr. Knotts.
You guys have any questions? How you starting this problem?
Dr. Knotts, we did have a question.
Okay.
So we're doing number 2, and it talks about how it's a cross flow heat exchanger.
Yep.
So do you have to do delta T log mean differently since the temperatures are their inlet and outlets are different?
How do we change in the delta T log mean? How do you change from different heat exchangers like multi-pass or cross flow or things like that? You remember?
Oh, it's with the F value, right?
The F value. So there's an F value for cross flow. You'd have to look in your supplementary information. There's tables. Or you can use the epsilon NTU method. You could do both. Let's see, this one you're given 3 of the temperatures, so you could find the 4th one fairly easily just from m dot calculations, right? M dot CP delta T. So if you have your book there, if you look at a figure 11.14, it has a cross flow unmixed for epsilon NTU if you wanted to use that one. If you want to use the delta T log mean, then you have to calculate go find the F in the supplementary information.
So do you have to account for the fouling factor in the epsilon method, or is it just like accounted for because you use these different correlations instead?
It would be, so if you have a fouling factor, did I give you a fouling factor on this problem? I can't remember. If I give you a fouling factor for either method, you always just put it into UA. Right, it's another resistance in your UA equation. And so I think I give you a U in this case, so it's already doing all the H's, all the fouling factors for you. Does that make sense?
Yeah.
Okay. I'm gonna go check on some other groups.
I think this could be solved algebraically by substitution.
Maybe.
I'll get back to y'all on that in a minute or two. I'm gonna go work it out.
Yeah, do that, Will, because I feel like there should be a way to do that as well. So I will also.
This is the basis from I'm starting from if someone wants to get on that with me.
Where are you? Sorry, I can't see your screen.
Here,
Here,
it
I'm
should
going
be
to your
showing
screen.
me when I'm blathering.
Yep, I got it. Yep. Okay.
Sweet, you got it?
Yep. So 5.
Yeah, I got 0.06.
What the 6?
Rules. Okay.
Yeah, so I'm going to solve the first one for TH out and then input that into the second equation.
Oh, I see. Yeah, that's a good idea.
Hey, Dr. Knotts is eavesdropping on us.
I just wanted to.
Oh, good. I want him to
guys are
see me
okay.
being smart for once.
We have an answer. We don't know if the answer is correct, though.
Okay. I'll give you a little hint. What's your answer?
0.06.
I think that's, and you're in kilograms per second?
Yes.
I've got something a little lower or a little higher than that.
Did you get 0.376?
That's getting closer. What method are you using to solve this?
So what we did is we solved for the heat using, the total heat using CC times the change in temperature.
Yeah, m dot Cp delta T, good.
And then we divided by UA and then used a solver to get the outlet temperature.
Okay, what'd you get for the outlet temperature?
That's what we think is suspect. We got 31. That would be Kelvin.
Okay.
Or
No.
not Kelvin, Celsius.
31 Celsius, yeah.
Yeah, okay. I think you're okay then. So
I got 0.383, and we haven't talked amongst each other about why we have different answers.
Okay, I'll let you guys talk through then. I think you're okay up to your temperature, so that should be pretty easy to figure out.
Okay.
All you smart people got an easy one.
Yeah, seriously, it was dope.
Okay,
So,
I'm gonna go check on some other groups.
So Dakota, how did you get your 0.0006?
How's it going,
How
Dr.
are you guys doing?
We have the answer for the first part of the question.
You want to run it by me?
Sure, we got that the cold stream mass transfer was 759.6 kilograms per hour.
Are you on problem 1? Or
Problem five.
Oh, problem 5. Okay. Okay. Sorry. I was like, something's wait. Let's see. You got m dot cold. What did you get again?
759.6 kilograms per hour.
I got something way different than that. What'd you get for your Q?
Q 2.54 times 10 to the 7th joules per hour.
Okay. I don't know how you solved it. Did you check your units?
So our values aren't in watts; they're in joules per hour. Do you want us to put it in
Joules per hour? Okay, yeah. Let's see. What can you put it in watts?
Yeah.
I did it all by hand. So
Watts is 7,068.
okay.
That's what I got too.
Okay. And your m dot cold?
In per second?
Yeah, kilograms per second.
I'm getting 0.211.
Okay. I think you guys are on the right track then. Keep going. Make sure you get all the right same answer at the end, and I'll come check on you in a minute.
Okay. Thanks, Dr. Nuts. So for area, are you guys just doing pi dl to get the area?
Hey, group 6, just checking on you guys.
I think we're almost there, Dr. Nance.
Okay. You're doing problem number 1, right?
Correct.
Yes.
Okay. If you don't have any questions, then I will go check on the other groups, and I think we're getting close to being done. We'll come back here in a minute.
This is one very minor question. You mentioned that we could do these without like an fsolve or a Python or anything. The one thing we were running into was that we were trying to make the heat capacity of the water a function of the average temperature.
Yep.
So in order to get like a pretty exact answer, one of us had to do it in Python. Is that what you were looking for there?
So you could, if I was doing this by hand, I would guess a reasonable temperature out and get a heat capacity. And then you could check right then to see what it is, or you could say, because of time, I'm not going to iterate, but if I wanted to, I'd iterate right here on m.cp delta t to get a T out. That makes sense?
Yeah.
The nice thing about these calculations where you're trying to get a T out and you have all the other temperatures is heat capacity is not a huge function of temperature. So if you give it a good guess value, it's probably not going to need too much iteration. On that example I did in class several days ago, I kind of get it a pretty bad guess value. And so, but I think you guys are probably on the right track then. And I'm going to go check on the other groups and see where they are.
Sounds good. Thank you.
Okay.
Just have units of joules per mole. So when we multiply them through,
just divide by the molecular weight.
Yeah.
Water. Anyone remember the molecular weight of air again?
You
It's
can
in
just
the air
do
properties.
water properties.mw.
Or for air properties.
Air properties.
Hey, Bryson, did you have a question for me?
yeah, we all do.
We want to know if we're using the right NTU correlation.
So NTU, usually you'll either get it from a chart or you'll calculate it by UA over C min.
Yeah, I forgot it's UA over C min.
Okay.
Sorry about that.
Well, in fact, you got it on the next line there. So on this one, you're going to calculate an epsilon, or you're going to calculate a UA like you did, or you're going to calculate an NTU from your UA and your C min, right?
So Dr. Nuts, this is kind of why we're asking is because in table 11.4, it doesn't have one that's for both fluids unmixed. It only has one that where like one of the streams is mixed.
11.4 should be, oh, I'm looking at table 11.4 right now. And doesn't it say
Even though we're not given like
single
a
pass
certain number
cross
of
flow with
points.
both fluids unmixed?
It does on
No.
11.3, but then 11.4 it
Oh,
doesn't.
not equation. Go to, oh, I was looking at figure 11.14.
Oh.
11.14. You could use the equation. I see what you're doing now. So you would want to do, yeah, I don't know what that is. Go to figure 11.14 in your book, and it might be a little easier to pull off rather than using the equation. And it's for both fluids unmixed. Does that make sense? I'm going to go check out room 5. Send me another message in a couple minutes if you still need some help.
Okay, we will.
That changes like everything.
Hey, group 5. I think this is
Hey,
group 5.
can we check a length value with you?
Okay.
We got 4.93 meters.
You guys ready to sell your homework souls on that one?
Ooh, well, we could wait for a couple of our people
No.
to finish, and then we can sell our homework souls.
I think you're on the right track. I think you're close. So just as soon as you guys are ready, I'm checking it into the other groups. I think most people are finishing up.
Okay.
Okay.
Awesome.
I'm willing to put my homework soul on it.
Right. So then like my delta T2 would be T hot 2.
Hi, Dr. Knotts.
Hey, group 8, sorry. Is this group 8?
Yep.
Yes.
Okay. You guys feel okay?
Yeah, we think we got an answer.
Think.
Yeah.
Okay. Are you doing problem number 3? Is that what you're doing?
Yeah.
Yes.
Okay. What method did you use? LMTD or NTU?
LMTD.
Okay. And you knew all the temperatures, or you could get the third temperature fairly easily, right? Or the fourth temperature.
Yes.
Mhm.
Good. Okay. So you ready to sell your homework souls on there?
Ooh.
With your answer?
No, are we guys?
Well, like all of us got the same thing.
Okay. Then I'm going to check on the other groups, and we'll be together here just a few minutes.
Cool.
Hey,
But
group
it'd be a
9.
whole. Oh, hey, is that Professor Knotts?
Yeah, I'm just checking in on you guys.
Okay.
You guys feel like you've got it settled?
For problem 4, yes.
Okay. You ready to
In
sell
like
your
the first
homework
3
souls
minutes.
on problem 4?
Who has the Python notebook for that?
I can do it. I have mine.
Okay.
And so this one, you were given all but 3 temperature, or all 3 temperatures. You could get the fourth one fairly easily from m.cp delta T. And then, or no, you could get Q. You're not given, you can get Q fairly easily. Okay. And what did you guys get?
VO4 Kelvin and 0.38
Okay.
kilograms per second.
You feel pretty confident about that one?
Yep.
Yeah.
Okay. I'm going to check couple more groups, and then we'll be back soon.
Okay.
Dr. Knotts, are you on?
I'm here.
I just had a couple of quick questions for you. So I got your email. Are you saying, so on Friday, is there home over the weekend?
Kyle, you're cutting in and out. I'm not sure why, but there is no homework on Friday.
Okay, and assuming we get all of these problems right as a class, is there homework today?
There's no homework today if you get them all right.
Gotcha, thanks.
We're almost done. Make sure someone in your group's ready to talk through your problems when we all get back together.
Oh, just like that. Look at that. There he is.
Okay, group 1.
Hey, we just had a question. So we're looking for like the CP of oil because we think we need that.
Okay.
Do we need that?
You do?
Okay, cool. Does this seem like a reasonable number? 2.118 kilojoule per
Yeah, and then you're
kilogram
doing
per
the
Kelvin.
unit conversions with your units thing. Okay.
Yeah.
Yep. I think there's only one oil in the back of the book, right?
Oh, we didn't find it in the back of the book. We found it on Google.
No, this number comes from the back of the book.
Oh, it does?
I got that one from the saturated liquids table.
Fun.
Yeah.
It does come from the back of the book.
Yeah, so we're getting a length of like 46 meters for this heat exchanger. Does that seem reasonable?
Do you guys all get there? Kind of the same thing?
Yep.
Yeah.
Then let's go with it. I'm going to check a couple other rooms and then we'll get back together. Have someone ready to share your screen when we talk through them.
Okay.
Okay.
Check to see if the units work out then.
Okay, I can't remember what group this is, but I think someone asked me in.
This is group 2. We invited you. So we're working on the second problem, and we have come to an answer for the surface area of this.
Yep, that works out.
We can show you our work if you. I guess I think you can see the screen.
So do you all agree on the method?
Yeah, we made sure that we were all caught up and on the same page.
Okay.
With finding the NTU and then using that to get the surface area.
And you got a 0.7 for your epsilon, so I think you're on the right track.
And our area that we got is 1.5,
okay.
1.6 meters squared.
You ready to sell your homework souls on that one?
Yeah.
Okay.
Put my degree on it.
Oh, hey, I
Oh,
will.
shoot.
I got to check 2 more groups and then we'll probably be back.
Okay.
Okay, give me a second here.
Did we get it right? Or
Group 10. Are you there?
I think I'm the only one here.
Okay, Sterling, let's see. I'll assign you to one of the groups here for a second, but we're almost ready to come back.
Okay. I think everybody went back already. I just didn't
Oh.
realize it. I was still working on the problem.
Okay. So are you guys from group 10? It looks like you guys have already broken up your group.
Yeah, we finished.
Okay. I don't know if you saw the email. I just said we got about 2 more minutes, maybe about 1 more minute now, and then everyone will be back.
Okay.
Okay, I think everyone should be back now. Let's see, groups 1 and 6. What did you guys get for your answer for problem 1? And then I'll show you the key on groups 1 and 6. Anybody?
So for group 1, we got the outlet temperature of the water, which wasn't asked for.
Sorry, I think this one did. Who said that?
Sorry, I let go of the space bar.
Oh.
So the length of the heat exchanger would be 46 meters, and then we also solved for the temperature of the cold stream out, being about 320 Kelvin.
Okay.
Yeah, that's what group 6 got as well.
Okay. Do you got about 320 Kelvin also?
Correct.
Did you guys iterate on that, or did you just guess and go with it?
We use Python.
Okay. I guessed, and I got very close to your answers, and I got 46 meters. So let me show you that. Let me share my screen. Okay, sorry, it's taking me a second. Okay, everyone see that now? Problem number 1. So let's just go over this. I want to talk through a couple things real quick. On this one, you know the inlet temperature of the cold and the 2 other temperatures. You also know both flow rates. And so you can get the other temperature fairly easily just using m.cp delta T. That should almost always be kind of your first thing that you do on these problems, is just use the thermo equations to see if you can set all the temperatures. That becomes problematic if you don't know a flow rate or if you don't know 2 of the temperatures, because then you've got to solve 2 equations, 2 unknowns. But the first thing you should do is then use m.cp delta T to get a new temperature. You see that I guessed something so that my T cold out was about 310. And I assumed water at 305, and the properties work out that you don't have to iterate much. And this one, notice that on all these problems, if you haven't noticed, is I don't make it so that you have to calculate H's. I've given you the U's, and I will do that. I will test whether you know U's, maybe other problems, or if you do, I won't make you get a correlation on a hand-like problem. I would give you H's or something like that. At least that's how I think of it. That's how I've done it in the past. But what makes these easy, right, is that you don't have to solve an H out or a U out. I give you those, and so areas like separated out. There's no hard correlations that are dependent on L or the length.
Where did you get the heat capacity of the oil?
So I just looked in the back of the book. There's something called oil. It just says oil. And I just picked it up there.
Okay.
All the properties, if I give you a hand calculation like that, it's going to be in the back of the book.
Dr.
Okay.
Max, are you going to post the keys for these?
Yep, I'll post the keys. I'm just not going to do it until I know you get them all right. Problem number 2, probably the hardest, because there was a little new thing. We talked about a cross-flow heat exchanger with no mixing. Who in groups 2 and 7? Who wants to volunteer to tell me what you got?
Group 2 got 1.57 meters squared.
Okay. And group 7, you guys want to volunteer to see if you back that up?
We got 0.027 meters squared.
Okay, which one you want to go with, you guys?
Keep in mind it was a group effort.
I don't think, I think there was something wrong with ours. Like,
is that group 7?
Yeah.
Let me show you.
We're pretty
Here,
confident in group 2.
Okay. Here's what we're going to do. So I give you inlet temperatures, and I also give you a U value. You don't have outlet temperatures here. Oh, you do have one outlet temperature, so you can get the other's temperature fairly easily. So again, I kind of guess to get the heat capacities, I use Cp equals m dot Cp delta T, and this is what I get for my other cold temperature. This one, I used epsilon NTU because to deal with delta T log mean and crossflow, you have to get an F value. The F values are not in your book, they're in the supplement of your book, so you could go get those. But it just seemed a little easier to do the epsilon NTU method. And so you can calculate an epsilon because you know Q and Q max. I go then to figure 1114, I get an epsilon of 0.7, use that to get an NTU of about 1.5. Or if you use the equation, you get 1.44, and you get about 1.5 or 1.6 meters squared. So I'll give that one to you. The point with this is if you have a complex geometry, the book has all of the charts in it already. I'm going to bring that up real quick in chapter 11. You can use the equations, but if you're on a time crunch, like on a final exam, and I'm going to be very liberal giving you, I don't want you to have to iterate or do really complex equations like in tables 11.3 and 11.4. So let's just look here for a second in section 11.4, where it talks about effectiveness NTU method. It's almost there. There we go. So you can use these equations in table 11.3 and 11.4 to get epsilons or NTUs, but these same equations are in these tables right here. And on a time crunch situation, it would just be easier to pick off a table. So either you'll have an epsilon and a C min over C max, and you'll pick off an NTU, or you'll have an NTU and a CR over C max, or CR, C min over C max, and get an epsilon. And right here, you can see we have this cross flow, both streams unmixed. Figure 11.14. And so I just went to this chart, picked one off, and got it. Okay, problem 3. So group 3 or group 8. I think this was probably the easiest problem.
Group 8 got 49.9 meters squared.
Okay.
Group 3 got the same.
Okay, here it is. This one's probably the smallest. I'll just zoom in the whole thing. I give you 3 of the temperatures again. You can get the 4th one with Cp delta T log mean if you wanted to, or Cp delta T if you wanted to do the log mean temperature difference method. But it's pretty easy to do the epsilon NTU method here because you don't really need to ever calculate the outlet temperature in this case. So I can estimate a C min and a C max, get the epsilon, go to the equation or go to the chart, get an NTU, and then solve for area. How did you guys do it? Did you use delta T log mean or did you use NTU?
We use delta T log mean.
Okay, so you can see that we're getting the same answers with no matter what method you use. Okay, group 4 or group 9. This was probably the other, let's see, no, this one you might have to iterate a little bit to get temperature if you use delta T log mean. Group 4 or group 9?
We got 0.383 as the M dot.
Okay, and we're selling our homework souls on that one?
I guess, yeah.
Okay.
I don't know the other group's not answering.
Is the other group got that too? Let's talk about this one for a second. I won't show you the answer just yet. Given 3 temperatures again, and you're given a UA in this case, and you need to calculate an M dot. M dot's one of the hardest things to calculate. If I was doing this on a homework, you'd have to do a huge F-solve block because almost everything's dependent on M dot. Now, it gets a little easier because I give you UA, so you don't have to use that M dot to get H's. But notice that anytime I give you UA, it gets a little easier. So in this one, you can calculate Q using M dot Cp delta T. And then you could calculate an outlet temperature on the other side by using UA delta T log mean, or you could use Q's, or you could do a variety of things. Oh, you can't use Q as M dot Cp delta T because you don't know M. You had to use this or epsilon NTU. And this problem, one equation, one unknown, I threw it in my calculator and got 31.1. And then you can determine m dot. So I got 0.38.
Way to be group 4.
Good job. And then let's groups 5 and 10. Who wants to chime in and see if they got this one?
Yeah, we got 0.211 kilograms per second and 4.93 meters.
And group 10 got the same thing.
Okay, that's what I got. So no homework today, but let's talk through this one more thing. Here I give you all the outlet temperatures, and let's just use these last couple minutes to talk about, if you're doing this by hand, if you have all the temperatures, it's fairly easy to do delta T log mean, because I can calculate delta T log mean directly, and it usually means I'm looking for an area or a length or something like that, the geometry. If I don't have all the temperatures, it's usually easier to do epsilon NTU by hand. And you can go through these problems and see how that was done. I give you little hints on this. I'll post this key. I'm not going to post it until after. You need to post whatever homework you did, whatever work you did, take a picture of it, whatever, and post it to the homework 30 as your assignment today. Anyone that wasn't in class today is going to have to do one of these by hand and then post it. Does that make sense for everyone?
So Dr. Knotts, my work for the one I did is kind of sporadic just because it's more scratch work. Should I clean it up or?
Nope, we're not even going to grade them. I just want you to know, I want you to post them right now, as soon as, or you can do it right now or just within 10 minutes after class. Take a picture of this screen right here if you didn't write anything down and just post it. And so I'll give everyone a second before I do that. I just kind of like an attendance. I just want you to do it for attendance. If you were here, I'm going to give you credit for it.
And that's for homework 30, you said?
Homework 30. You should just be able to post that one thing on Learning Suite.
Is this just problem number 4 or our
you only have to do one of them. So if you didn't write anything down for your problem, just take a screenshot of this or whatever. Picture camera, picture of this, and I'll give you credit. I just basically
wait. So you want us to upload something even if we did attend class?
Yep. I would just want you to upload either a picture of this or whatever work you did, just as like an assignment, just like as an attendance type quiz, and just do it right now. Let's talk about what's going to happen next time while you're doing that. There's going to be no homework assigned, but we are going to have a quiz, and it's going to be fairly similar to these types of homework. And so make sure you kind of go over the keys. I'll make sure I post those, and I'll post them within just a few minutes after I send some email out to the rest of the class. And then I'm going to show you what's called a simulator. There's different chemical engineering simulators, chemical process simulators that do most of the calculations you guys do in classes. Heat exchangers, just pumps, all sorts of things. And I'm going to show you how this is done on a simulator next time. I'm not going to give you homework on that because it's kind of hard to get it to work over the internet. I tried getting it to work and I couldn't, but I still want to show you how you would do this in industry. You won't remember it unless you're doing it anyway, but I'll post some helps, and there's all sorts of video things online. But I mainly want to show you how you got to know about things like UAs and H's and fouling, and you got to know M dots and things like that. So you can take and see that even though we've been doing these things by hand, and now you kind of know how to do them by hand, in the future you're not going to do them by hand. So there will be no homework on Friday. There will be a quiz in class, so make sure you show up. Let's see, someone just raised their hand. I know who it was. I didn't quite catch it. No, I can't see.
It was me.
Okay, go ahead.
So I was just wondering, do we have to do any homework time quiz?
No, no homework time quiz for this. I didn't even set one up. So just post your assignment, post a screen capture, post whatever from this lecture, and you're done for the day. You can see that you have some competency quizzes you could work on if you want to for heat exchangers. You have you can work on your project if you need time for that. You can just study and get caught up on heat exchangers. And then we'll do the same thing because it's conference this Friday. but use this time to make sure that you're figuring out heat exchangers so that you're ready for the final exam. After conference on Monday, we'll do one more day of heat exchangers qualitatively, and then we'll start radiation. Okay. Any questions before we sign off? Great. Then I will see you guys on Friday in class.
Thanks, Dr. Knotts.
You're welcome. Good job today.
Muito obrigado.
Thanks.
You're welcome.